12.2 Lesson 1, Differentiation of Vector-Valued Functions. Our objectives for today are 1. You will see the relationship between the definitions of the derivative of a real-valued function that you learned early on in Calculus AB and the definition of the derivative of a vector-valued function. You will be able to, objective 2 is you'll be able to find the derivative of a vector-valued function. So let's begin by reviewing the definition of the derivative of a real-valued function. Here we have the definition of the derivative of a real-valued function. The derivative of a real-valued function f. For example, if you happen to have f of x is equal to x squared, at x is given by f prime of x. It is defined as the limit of this difference quotient as delta x approaches 0. If that limit exists, we say the function f is differentiable for all x at which this limit exists. For all x for which the limit exists, f prime representing the derivative function is a function of x. So let's understand this definition graphically. So here we have the graph of f of x is equal to x squared. It is, of course, a parabola. And let's see if we can make sense of this difference quotient from the definition of the derivative. The difference quotient has a numerator and a denominator. And if you look at the numerator, it is a difference of output values from the function f. So you're taking the output value at the input x plus delta x and subtracting from it the output value of the function at the input x. Or it is, in fact, the change in y. So the numerator of this difference quotient is giving you a change in y. And the denominator is, of course, a change in x. And the way you get that is just by subtracting the input values. If you do x plus delta x minus x minus x is 0, leaving you with just delta x. So what is this? From algebra, we know that the change in y divided by the change in x will give us the slope of a line passing through these 2 points. And this is, of course, called the secant line through these 2 points. And what are we doing with this limit? We're taking the limit of this difference quotient, which gives us the slope of the secant line through the 2 points as delta x approaches 0. And delta x represents the change in x as we go from, let's say, point A to point B. As we go from point A to point B, delta x represents the change in x. In other words, how much more or less is the x coordinate of point B compared to the x coordinate of point A. And if delta x is approaching 0, that means the difference between the x coordinates is becoming negligible. It's becoming less and less. Physically, that means point B will be closer and closer to point A. So what happens as point B moves closer to point A? The slopes of the secant lines through points A and B will begin to approach a limiting value, and the limit of the slopes of the secant lines as point B approaches point A is defined to be the slope of the tangent line to the graph of f at point A. So the slope of the tangent line to the graph of f at point A is defined to be the limiting value of the slopes of the secant lines as the second point moves closer and closer and closer to the first point. So we may also understand, so we understood this definition from a graphical perspective. You can also understand this definition from the perspective of rates of change. So this is the rate of change of one quantity with respect to another. This is the average rate of change of one quantity with respect to another. For example, if we talk about the change of velocity with respect to time, we're talking about the average acceleration, which is, of course, the derivative of the velocity function. And when you take the limit of the average rate of change as delta x or delta t approaches 0, you are talking about the instantaneous rate of change, for example, of velocity with respect to time, which would be the instantaneous acceleration. So this is what we learned about derivatives in Calculus AB. And let's take a look at how we can apply this particular definition to find the derivative of f of x is equal to x squared. So we begin with the definition of the derivative, and now we're going to recognize that this definition has three parts to it. The real easy part is the denominator, it's just delta x. The second easy part is f of x, in our case, just x squared. And the third part is something that you need to understand. You're going to evaluate whatever your function is at the input of x plus delta x. So if our function is x squared, we're going to have the input x plus delta x, and you're going to square that. So the rule for the function is to square the input. So we're going to do that. And then we have minus f of x, which is just x squared. All of that over delta x. So now we have the limit as delta x approaches 0. How do you do the part that I wrote in red? You have to do FOIL, and when you do that you get x squared plus 2x delta x plus delta x squared, and then you have minus x squared, all of that over delta x. So one thing that you'll notice is that you will have x squared minus x squared, which is 0. And that would leave us with the limit as delta x approaches 0 of (2x delta x plus delta x squared over delta x). And one thing that you can notice is that in the numerator, both terms have a common factor of delta x. So you can factor out delta x from each term. And when you do that, this is what you will have. And of course, you can cancel the common factor of delta x, because delta x is not equal to 0. It is only approaching 0, so you can cancel non-zero common factors. And when you do that, this is what you have. You have the limit as delta x approaches 0 of 2x plus delta x. And you can evaluate this limit by direct substitution. Replace delta x with 0, and you get that the limit is 2x. So the derivative of the function f of x is equal to x squared is 2x. Later, after you learned this definition, you learned about some differentiation rules, all of which are based on this definition. So for example, you learned about the power rule for differentiation. Whenever you have a power function, such as f of x is equal to x squared, it is easy for you to take the derivative. How do you do that? You're just going to take the exponent and bring it to the front. And of course, that would give you 2x. So you might be asking, why did you have to use this particular definition to get 2x when you can just use the power rule? The answer is the power rule is based on this definition. All right, so now we're going to go ahead and take a look at, but of course, once you have the power rule, you don't have to do this. You can just get f of x is equal to x squared and f prime of x is equal to 2x by using the power rule, which is established by using this definition of the derivative of a function. In Objective 1, we'd like to see the relationship between the definitions of the derivative of a real valued function, which we just reviewed, and the definition of the derivative of a vector valued function. So let's compare the two definitions. So we just reviewed the definition of the derivative of a real valued function. The derivative of f at x is given by the limit of this difference quotient as delta x approaches 0, provided the limit exists. For all x for which the limit exists, f prime is a function of x. So now let's look at the definition of the derivative of a vector valued function. The derivative of a vector valued function r is defined by the limit of a difference quotient, just like you saw with real valued functions. And if you look at the difference quotient, what are we doing? in the definition of the derivative of a real valued function, in the numerator we have the function evaluated at the input x plus delta x. With vector valued functions, we are using delta t, so the input will be t plus delta t, but we're evaluating our vector valued function at the input t plus delta t. And then with the real valued function, you had minus the function in the numerator. Same here with vector valued functions, minus the vector valued function in the numerator. With the real valued functions, you had divided by the change in x, and you're of course taking the limit as the change in x was approaching 0. And with vector valued functions, you have divided by the change in t, and of course you're taking the limit as the change in t approaches 0. So you see that the definition of the derivative of a vector valued function is like the definition of the derivative of a real valued function. It is the limit of a difference quotient as delta t approaches 0. So the derivative of a vector valued function r is defined by the limit of the difference quotient as delta t approaches 0 for all t for which the limit exists. If r prime of c exists, then we say the vector valued function r is differentiable at t is equal to c. If r prime of c exists for all c in an open interval I, we say the vector valued function r is differentiable on the interval I. Differentiability of vector valued functions can be extended to closed intervals by considering one-sided limits. So now what we want to do is we want to think about, okay, so this is the definition of a vector valued function. So let's see if we can apply it to come up with a way of finding derivatives of vector valued functions easily. So here we have the definition of the derivative of a vector valued function, and let's consider a vector valued function r of t as shown here. So f of t and g of t are real valued functions. They are the component functions of our vector valued function r of t. For example, we could have r of t is equal to ti plus t squared j. So f of t would be just t, and g of t would be t squared. These are called component functions. But of course we want to do what we're about to do for the general vector valued function r of t, where the component functions could be whatever real valued functions you choose. So now what are we going to do? How do we start finding the derivative of r prime of t? You have to start with what we mean by the derivative, which is the limit of the difference quotient that you see from the definition. So we start with that definition right here. And again, just like we saw with real valued functions, you're going to have to look at the difference quotient one part at a time. So you have delta t in the denominator. That's the easy part. And then you have minus r of t. That's not really a problem either. Where do we have that? Minus r of t would be, this is r of t, so that would give you minus f of ti, and if you distribute the minus sign to the j component, that will give you minus g of tj. So that's not bad. And the last part that we need to focus on would be r of t plus delta t. What is r of t plus delta t? Well, here's our function r of t. So you're going to evaluate your function when the input is t plus delta t. So you're going to have f of t plus delta ti plus g of t plus delta tj. So that's what we have, and we're going to take the limit of this difference quotient as delta t approaches 0. So how do we do that? We want to do some rearrangement of the terms that we have for this particular line. Specifically, what we want to do is we want to put the like components together. So the like components are the I components, and of course the J components are like components as well. So when we put those together, we get the following. We're still taking the limit as delta t approaches 0, but when we put the I components together, we have f of t plus delta t minus f of t, and then we can factor out the standard unit vector I, and then all of that divided by delta t. Of course, here you have a fraction, and delta t is the common denominator, so now you can write it as a sum of two fractions with the denominator delta t. And when you do that, and you're going to have g of t plus delta t minus g of t, and you can factor out the standard unit vector j, and you have that over the denominator of delta t. So what do we do next? What do we do next? What we do next is we're going to go ahead and use a property of limits. What you have here is the limit of a sum. So you can write that as a sum of two limits. So here's the first limit, and here's the second limit. So you have the sum of two limits. And what are we going to do? For the first limit, take a look at what you have here. You have the standard unit vector I here. But remember, when we're talking about a vector-valued function, each of our component functions are real-valued functions. So for example, with our specific example, f of t is equal to t, and g of t is equal to t squared. Those are real-valued functions. So what you have here at this particular point is you have the standard unit vector I and the standard unit vector j, just like you have here with our specific example. But each of them are being multiplied by a real valued function, f and g. And what you have here is the limit as delta t approaches 0 of the difference quotient f of t plus delta t minus f of t over delta t. And you will remember from the definition of the derivative of a real-valued function that we just reviewed from calculus AB that this is just the derivative of the function f, if that limit exists. And the same here. You have the limit as delta t approaches 0 of the difference quotient g of t plus delta t minus g of t over delta t. And that limit is the derivative of the function g prime of t, and we have f prime of t times the standard unit vector I plus g prime of t times the standard unit vector j. And here we are. This is the derivative of the vector-valued function r, and what that shows you is that to find the derivative of a vector-valued function, what do you need to do? Quite simply, you need to do the following. If your vector-valued function r of t is equal to some component function f of t times the standard unit vector I plus some component function g of t times the standard unit vector j, where f of t and g of t are real-valued functions, the derivative of the vector-valued function r of t is r prime of t, and it is simply the derivative of the real-valued function f times the standard unit vector I plus the derivative of the real-valued function g times the standard unit vector j. So let's see that with our specific example here. All you have to do to find the derivative of this vector-valued function r of t, where r of t is equal to ti plus t squared j, is the following. R prime of t is equal to the derivative of t with respect to t is 1, so you just have 1I, plus the derivative of t squared with respect to t is 2t, so you have 2tj. So that's all you have to do. to find the derivative of a vector-valued function, you're going to find the derivatives of each of your component functions and then multiply by the standard unit vectors respectively and have a linear combination of these multiples of the standard unit vectors I and j. So how do you find the derivative of a vector-valued function? You find it on a component-by-component basis. We just derived and demonstrated this theorem, Theorem 12.1, differentiation of vector-valued functions. If you have a vector-valued function r of t is equal to f of ti plus g of tj, where f and g are differentiable functions of t, they are real-valued functions, they are the component functions, then the derivative of the vector-valued function is find the derivative of f, multiply by the standard unit vector I, and add to that the derivative of g multiplied by the standard unit vector j. And the second rule here is the same thing, but it's just for space vectors where you have a third component. So here's a very quick example. How do you find the derivative of this vector-valued function? You would take the derivative of the component function sine of t, which gives you cosine of t, multiply that by I, and take the derivative of the component function cosine, which gives you negative sine. So you have plus negative sine of t, multiply that by the function j. So one thing that you'll notice is that the derivative, I need to have the notation for the derivative. The derivative of a vector-valued function, so this is the prime notation, it is also a vector-valued function. The derivative of a vector-valued function is a vector. It is a vector-valued function. We would now like to take a look at number 1 and apply what we've been discussing to do number 1. In exercises 1 through 6, sketch the plane curve represented by the vector-valued function. So for number 1, we have r of t is equal to t squared I plus tj. Sketch the plane curve represented by the vector-valued function and sketch the vectors r of t naught. So the vector-valued function r evaluated at t naught and r prime of t naught. So sketch the vectors r of t naught and r prime of t naught for the given value of t naught, which is 2. Position the vectors such that the initial point of r of t naught is at the origin and the initial point of r prime of t naught is at the terminal point of r of t naught. What is the relationship between r prime of t naught and the curve? And this is something that we want to focus on, because this is an application or something that we can, it's an application. It's an application of the derivative of a vector-valued function. So let's look at that. The first thing that we want to do is sketch the plane curve represented by the vector-valued function. As we had discussed in a lesson for 12.1, there are different ways you can do that. One of the ways is to actually evaluate the vector-valued function at different values of t, and the output for each input value of t will be a vector, and you will draw each vector in standard position, and the terminal points of the vectors drawn in standard position will trace points on the curve of r of t. And if you follow the increasing values of t, you will get the orientation of the curve. Alternatively, you can write this vector-valued function as a set of parametric equations, and it will give you the same curve with the same information for the orientation. You could even eliminate the parameter from your set of parametric equations and get the rectangular equation for r of t. So we will follow the first approach. I would like to remind you that you can also write a vector in component form like this. So you can have it as t squared comma t. And I'd like to go ahead and represent the output values from my vector-valued function in component form. So I have negative 2 squared is 4 for the horizontal component, and for the vertical component, it is whatever t is. So if I do that with the other input values, negative 1, 0, 1, and 2, these are the output values I get from my vector valued function. Notice that the outputs are vectors. The outputs are vectors. So I have negative 1 squared is 1, comma, negative 1, 0 squared is 0, comma, 0, 1 squared is 1, comma, 0, 2 squared is 4, comma, 2. 1 squared is 1, comma, 1, 2 squared is 4, comma, 2. And each of the outputs are vectors. And as I was saying, you can sketch each vector in standard position with the initial point at the origin. So we have 4, negative 2. And then we have 1, negative 1. And then we have the 0 vector, which is just a point at the origin. We have 1, 1. And then we have 4, 2. So the terminal points of these vectors sketched in standard position are points on the curve. And the orientation of the curve will be, as you see me sketch it right now, that's the orientation of the curve. And it just goes on from there. So to indicate the orientation, I'll use arrowheads. And this is what we have. So let's continue reading the instructions. It says, sketch the vectors r of t naught. In our problem, the given value for t naught is 2. So r of t naught is the vector 4, 2. And I already sketched it. This is the vector r of 2. R of 2 is equal to 4, 2. And I already sketched it. It's right there. Let me go ahead and highlight it in a different color, gold. So it says here, sketch the vectors r of t naught and r prime of t naught. So now we need to find the vector r prime of t. So the vector r of t in component form would be t squared, comma t. So when you want to find the derivative of that, you're going to differentiate on a component by component basis. So you'll have 2t, comma, 1. So it says here, sketch the vectors r of 2, t naught is 2 in our problem, and r prime of 2. So what is r prime of 2? So r prime of 2 would be 2 times 2, which is 4, and then 1 is just a constant. So r prime of 2 is the vector 4, 1. Sketch the vectors r of 2 and r prime of 2 for the given value of t, which in our case is 2. Position the vectors such that the initial point of r of 2 is at the origin. We already have that right here. The initial point of r of 2 is at the origin. And the initial point of r prime of 2, which we want to look at next, here's r prime of 2. The initial point of r prime of 2 is at the terminal point of r of 2. So here's the terminal point of r of 2, which is the point on our curve corresponding to t is equal to 2. So now we want to position the vector r prime of 2 so that the initial point of r prime of 2 is at the terminal point of r of 2. So now I will go ahead and do that. So I have 4, 1 for r prime of 2. So from this point, I will go 4 units to the right and 1 unit up. So here's my vector, and this is the vector r prime of 2 equal to 4, comma 1. Now we want to focus on the question, what is the relationship between r prime of 2 and the curve? Well, here's the vector r prime of 2, and how is it related to the curve? The curve is the green curve, and you can see that the vector r prime of 2 is tangent to our curve at the point corresponding to t is equal to 2. And if you go back to the definition of the derivative of a real valued function and the graphical interpretation of that derivative, it gave us a tangent. The derivative of a real valued function gave us the slope of the tangent line to a curve at a particular point. And we see the same thing here with the derivative of a vector valued function. It is giving us the tangent, a vector that is tangent to our curve at the particular value of t. And if you consider this in the context of a motion problem, where you have a particle moving in the xy plane, where the position of the particle is given by r of t, then r prime of t would give you the velocity vectors at different times. And remember, velocity is a vector because it has direction and magnitude. And now, because we're using vector valued functions, and you sketch the vector r prime of 2, it has a particular direction and it has a particular magnitude as given by the length of the vector. So this tells you, the vector r prime of 2 tells you the direction that the particle is moving in at a particular instant in time, and also the magnitude of the vector would tell you the speed of the particle at that instant in time. So you get two pieces of information, not only the magnitude, which tells you how fast the particle is moving at that particular instant in time, but also the direction that the particle is moving in at that particular time. So that is an application type of problem where the original vector valued function would give you the position of a particle moving in the xy plane at a particular time, and r prime would give you the velocity of the particle at a particular instant in time, and the velocity has both direction and magnitude, and that is why it is appropriately represented by a vector. Today we looked at the relationship between the definitions of the derivative of a real valued function and the derivative of a vector valued function. And we also found the derivative of a vector valued function by differentiating our vector valued function on a component by component basis.